Among the many physical laws that quietly govern the universe, few are as influential as the speed at which light moves through empty space. This speed, close to 300,000 kilometers per second, is more than a simple measure of motion. It is woven deeply into the fabric of reality, linking time, space, energy, and matter in ways that are subtle, consistent, and often surprising. The story of how humanity came to understand this constant spans centuries of observation, experimentation, and theoretical insight. It begins with observations of celestial bodies and progresses through careful laboratory measurements, eventually leading to a gradual reimagining of how we conceive of the universe's structure. Along this journey, scientists discovered that light speed is not merely fast, but occupies a special role in the cosmos, one that determines the boundaries of causality and shapes the relationship between different reference frames in motion. For much of recorded history, the prevailing assumption held that light moved instantaneously from source to observer. This belief made intuitive sense based on everyday experience. When illumination fills a room after activating a lamp, no perceptible delay occurs. Lightning flashes appear to arrive the moment they occur, while thunder's arrival clearly takes time. These observations led many ancient thinkers to conclude that light required no time for its journey. In the early Greek philosophical tradition, Empedocles proposed around the 5th century, before the Common Era, that light must be something in motion, and therefore must take time to traverse distances. However, Aristotle's contrary view that light propagation was instantaneous carried greater weight in Western intellectual tradition. For over 2 millennia, Aristotle's perspective dominated scientific thought on this matter. In the Islamic scholarly tradition, the polymath known as Al-Hasan wrote extensively about optics in the 11th century. His work suggested that light travels at finite speeds that vary depending on the medium through which it passes. These ideas represented remarkable insight for their era. Though without experimental verification, they remained in the realm of theoretical speculation. The first documented attempt to measure light speed came from Galileo Galilei in the 17th century. His approach involved 2 observers stationed on distant hills, each holding a covered lantern. The first observer would uncover their lantern, and upon seeing this flash, the second observer would uncover theirs. By measuring the elapsed time for this round trip, Galileo hoped to calculate light's velocity. The experiment detected no measurable delay. Galileo correctly concluded that light must travel extraordinarily rapidly, though he could not determine whether it was truly instantaneous or simply too fast for his method to measure. The fundamental limitation was that human reaction times, measured in fractions of a second, were vastly longer than the actual time light required to travel the distances involved. Light crosses a kilometer in roughly 3 microseconds, while human responses take approximately 200,000 microseconds. The mismatch in scales made the measurement impossible with the available technology. The breakthrough in measuring light speed came not from earthbound experiments, but from astronomical observation. Ole Rømer, a Danish astronomer working at the Paris Observatory in the 1670s, was tasked with creating precise predictions for when Jupiter's moon Io would pass behind the planet. These eclipses occurred with remarkable regularity and were valuable for maritime navigation, as accurate astronomical tables helped sailors determine their longitude at sea. As Römer compiled observations over months and years, he noticed a pattern in the timing discrepancies. When Earth's orbit carried it toward Jupiter, the eclipses seemed to occur earlier than predicted. When Earth moved away from Jupiter in its orbit, the eclipses appeared to happen later. The cumulative effect of these timing differences over a full year was significant. Römer realized that these variations had a simple explanation. Light required time to travel across space. When Earth was closer to Jupiter, the light from Io's eclipse had less distance to cover, so observers saw it sooner. When Earth was farther away, the light needed additional time to cross the greater distance. The eclipses themselves were happening on schedule. The apparent timing shifts were due to the variable distance the light had to traverse. In November 1676, Römer made a prediction that demonstrated his understanding. He calculated that an upcoming eclipse of Io would occur 10 minutes later than standard tables suggested. Astronomers observed the eclipse at precisely the predicted time, confirming Römer's hypothesis. This represented the first successful determination of light's finite speed in human history. Römer estimated that light took approximately 22 minutes to cross the diameter of Earth's orbit around the Sun. This yielded a speed calculation of roughly 220,000 kilometers per second. The value was imprecise because the exact dimensions of Earth's orbit were not yet accurately known, but Römer had proven the essential principle that light travels at a definite, measurable velocity. More than 5 decades passed before independent confirmation arrived through a different method. In 1728, English astronomer James Bradley discovered stellar aberration while attempting to measure stellar parallax. Bradley was searching for evidence of Earth's orbital motion through tiny apparent shifts in star positions, but what he found was something unexpected. Stars appeared to shift their positions by approximately 40 arcseconds over the course of a year, but the direction and timing of this shift did not match parallax. Instead, stars seemed displaced in the direction Earth was moving at any given moment. According to legend, Bradley understood the phenomenon while sailing on the Thames River. Noticing how the apparent wind direction changed with the boat's motion, even when the actual wind remained constant. The explanation involves the finite speed of light. When walking through falling snow, even if the flakes descend vertically, one must angle an umbrella forward because forward motion intercepts the falling snow. Starlight behaves similarly, appearing slightly displaced in the direction of Earth's motion through space. By measuring this angular displacement and knowing Earth's orbital velocity, Bradley calculated light speed at between 290,000 and 297,000 kilometers per second, remarkably close to modern values. During the 19th century, physicists developed methods to measure light speed using terrestrial equipment rather than astronomical distances. French physicist Hippolyte Fizeau designed an elegant apparatus in 1849. He positioned a light source on a tower in the Paris suburbs, with a mirror placed approximately 8.5 kilometers away. Between the source and mirror, he installed a rotating toothed wheel with 720 teeth. Light from the source passed between 2 teeth of the wheel, traveled to the distant mirror, reflected back, and returned to the wheel. If the wheel rotated at a specific speed, By the time the light completed its round trip, the wheel would have turned just enough for a tooth to block the returning light. By precisely adjusting the rotation rate, Fizeau could determine the speed at which this blocking occurred, and from this calculate light's velocity. His result of approximately 310,000 kilometers per second was somewhat high, but represented a triumph of experimental technique. For the first time, light's cosmic velocity had been measured without relying on planetary distances. The experiment demonstrated that fundamental cosmic properties could be determined through laboratory methods. Léon Foucault, who had collaborated with Fizeau, refined the technique using rotating mirrors instead of toothed wheels. In 1862, he achieved a measurement within 1% of the modern accepted value. More significantly, Foucault demonstrated in 1850 that light travels slower in water than in air. This observation provided crucial evidence in the long debate between particle and wave theories of light. Isaac Newton had proposed that light consisted of tiny particles, which he termed corpuscles. His theory predicted that these particles should accelerate when entering denser media like water, similar to how objects accelerate when falling toward Earth. The competing wave theory predicted the opposite, that light waves should slow down in denser materials, just as sound behaves differently in various media. Foucault's experimental demonstration that light indeed travels slower in water supported the wave interpretation over Newton's particle model. Even the greatest scientific minds can hold incorrect theories, and new experimental evidence must take precedence over established authority. Albert Michelson became obsessed with precision measurement of light speed. Born in 1852, he immigrated to America from Prussia as a young child and later received an appointment to the United States Naval Academy. His refinements to the rotating mirror technique yielded increasingly accurate values for light's velocity. However, Michelson's most famous experiment aimed not at measuring light speed directly, but at detecting Earth's motion through the luminiferous ether. In the late 19th century, physicists believed that light waves, like sound waves, required a medium for propagation. Since sound cannot travel through vacuum, they reasoned that light must propagate through some substance filling all of space. This hypothetical medium was called the ether. The ether was thought to possess peculiar properties. It needed sufficient rigidity to transmit light waves at enormous velocities, yet had to be fluid enough not to impede planetary motion. It filled all of space yet remained undetectable through ordinary means. If Earth moved through this ether while orbiting the Sun, then light should travel at slightly different speeds depending on direction, much as swimming upstream is slower than swimming downstream. Michelson designed an interferometer to detect these differences. The device split a beam of light into two perpendicular paths, reflected each beam off mirrors, then recombined them. If one path encountered resistance from the ether while the other did not, the recombined beams would be slightly out of phase, creating an interference pattern that could be measured with extreme precision. In 1887, Michelson partnered with Edward Morley, a chemistry professor, to conduct this experiment in Cleveland, Ohio. They mounted their interferometer on a large stone slab floating in mercury to isolate it from vibrations. The effective light path stretched about 11 meters through an arrangement of 16 mirrors, Their measurements revealed essentially nothing. The observed effect was less than 1/40th of what they expected if Earth moved through the ether. Michelson described the result as decidedly negative. This null result is often called the most famous failed experiment in scientific history. Michelson and Morley had set out to measure Earth's motion through the ether, and instead demonstrated that the ether appeared not to exist, or at least did not affect light in the anticipated manner. Light travelled at the same speed regardless of direction, regardless of Earth's motion through space, regardless of how carefully the measurements were conducted. This finding raised profound questions. If there was no ether, what carried light waves through empty space? Why did Earth's motion not affect light's measured velocity? Answering these questions would require reconceiving our understanding of space and time themselves. In 1983, the General Conference on Weights and Measures made a significant decision. Rather than continuing to measure light speed with ever-increasing precision, they simply defined it. The speed of light in vacuum was fixed at exactly 299,792.458 kilometers per second, with zero uncertainty. This might seem like an arbitrary declaration, but it reflected deep understanding. After centuries of progressively more accurate measurements, scientists recognized that light speed is not merely a number to be determined, but a fundamental constant woven into the structure of space-time. It made more sense to use this constant as a foundation for defining other units of measurement. The meter is now defined in terms of the distance light travels in a specific fraction of a second, rather than the other way around. In 1905, a 26-year-old man working at the Swiss Patent Office in Bern published 4 papers in a German physics journal. Albert Einstein had no university position, no laboratory, no research staff. He examined patent applications during weekdays and pursued theoretical physics in his spare time. That year became known as his miracle year. The first paper explained the photoelectric effect by proposing that light comes in discrete packets of energy, now called photons. The second provided mathematical proof of atomic existence through analysis of Brownian motion. The fourth, just 3 pages long, demonstrated the equivalence of mass and energy. But the third paper, titled On the Electrodynamics of Moving Bodies, would eventually revolutionize physics. Einstein had pondered a thought experiment since his teenage years. He imagined chasing a beam of light, trying to catch up to it and match its speed. What would the light look like from that perspective? According to Newtonian physics, one should see a frozen wave, a stationary electromagnetic field. But James Clerk Maxwell's equations describing electromagnetism forbade such a thing. Maxwell's mathematics demanded that electromagnetic waves always travel at a specific speed. Frozen light was not physically possible. This paradox troubled Einstein for roughly a decade. His eventual solution was radical. Perhaps the premise was wrong. Perhaps it was impossible to catch up to light at all. Perhaps light always travels at the same speed relative to any observer, regardless of that observer's motion. Einstein built his special theory of relativity on 2 fundamental postulates. The first states that the laws of physics are identical in all inertial reference frames, meaning all viewpoints that are not accelerating. If someone sits on a smoothly moving train with covered windows, no experiment performed inside the train can reveal whether the train is moving or stationary. all motion is relative. There exists no absolute state of rest. The second postulate declares that light always propagates through empty space at the same velocity regardless of the motion of the source or observer. Whether one moves toward a light source or away from it, whether the source approaches or recedes, light will always be measured traveling at the same speed. These two principles seem almost reasonable when stated individually. The first had been understood since Galileo's time. The second essentially described what the Michelson-Morley experiment had demonstrated. But together, they lead to consequences that contradict everyday intuition about how the world operates. Consider a scenario where someone aboard a train moving at half the speed of light activates a flashlight pointing forward. Common sense suggests that an observer on the platform should measure that light traveling at 1.5 times light speed, the sum of the train's velocity and light's velocity. After all, velocities normally add. If one walks forward on a moving bus, someone on the sidewalk sees the combined speed. But Einstein's second postulate says this cannot happen. The platform observer will measure that light beam traveling at exactly the speed of light, not 1.5 times that speed, the same value measured by someone aboard the train. For both observers to measure identical light speed despite their relative motion, time and space themselves must be flexible. Different observers experience time passing at different rates. Objects in motion contract in their direction of travel. Events that one observer sees as simultaneous may not be simultaneous for another observer. These are not measurement errors or instrument flaws. Time and space genuinely behave this way. Once Einstein's postulates are accepted, these consequences follow inevitably from the mathematics. The fourth paper Einstein published that year examined the relationship between mass and energy. In just 3 pages, he demonstrated that these are two forms of the same thing. The famous equation relating them, though not written in its familiar form in the original paper, shows that energy equals mass multiplied by the speed of light squared. The implications are profound. Mass can convert into energy. Energy can convert into mass. Because the speed of light squared is an enormous number, approximately 9 followed by 16 zeros in standard units, a tiny amount of mass contains tremendous energy. 1 kilogram of matter, if completely converted, would release roughly 90 quadrillion joules of energy, equivalent to a 20 megaton nuclear explosion. This equation explains stellar luminosity. Deep within the sun's core, hydrogen nuclei fuse to form helium. The resulting helium weighs slightly less than the hydrogen that created it. The missing mass becomes energy, radiating outward as the sunlight that warms Earth. The sun converts approximately 4 million tons of mass into energy every second and will continue this process for billions of years. The equation also explains nuclear fission and fusion reactions. When heavy atoms like uranium split, or when light atoms like hydrogen fuse, a small fraction of their mass transforms into energy. The atomic bomb detonated over Hiroshima converted less than 1 gram of matter into the explosion that devastated the city. Einstein's relativity paper initially received limited attention. He was an unknown patent clerk with no academic credentials. But German physicist Max Planck recognized its significance and published supporting analysis. Gradually, the scientific community came to understand what Einstein had accomplished. Recognition from the Nobel Committee took much longer. When Einstein finally received the prize in 1922 for work published in 1921, the citation mentioned only the photoelectric effect, not relativity. At his Nobel lecture, Einstein spoke entirely about relativity despite officially receiving the award for different work. Time dilation represents one of relativity's most counterintuitive consequences. When an object moves relative to an observer, its clock runs slower than the observer's clock. Not appears to run slower, but actually runs slower. A moving clock genuinely ticks more slowly than a stationary one. This is not an optical illusion. It is not a mechanical defect in the clock. It is not a measurement error. Time itself passes more slowly for moving objects. The mathematical description involves the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who derived these equations before Einstein, but did not fully understand their meaning. Lorentz thought he was describing how objects contract while moving through the ether. Einstein realized there was no ether, and the equations described something more fundamental about the nature of spacetime. The Lorentz factor depends on how fast something moves as a fraction of light speed. At everyday human velocities, this factor essentially equals 1, meaning time passes normally. But as speeds approach light's velocity, the factor grows larger and larger. At 50% of light speed, the Lorentz factor is approximately 1.15. For every year passing on Earth, slightly less than 11 months pass for someone traveling at that speed. At 90% of light speed, the factor reaches about 2.3. 1 year on Earth corresponds to roughly 5 months for the traveler. At 99% of light speed, the factor approaches 7. 1 Earth year equals approximately 52 days for someone moving that fast. At 99.99% of light speed, the factor is roughly 71. For every year on Earth, the traveler experiences about 5 days. At 99.9999% of light speed, the factor reaches approximately 700. 1 year on Earth becomes roughly 12.5 hours for the traveler. This is not theoretical speculation. It is measured reality, verified countless times in laboratories worldwide. The clocks aboard GPS satellites, the decay rates of particles in accelerators, the lifetimes of cosmic ray muons, all confirm that time dilation is real. A simple thought experiment called the light clock helps illustrate this phenomenon. Imagine a clock consisting of 2 mirrors with a beam of light bouncing between them. Each round trip represents 1 tick. If this clock is stationary relative to an observer, the light travels straight up and down between the mirrors. Now imagine the clock moving sideways at high speed relative to the observer. From the observer's perspective, the light no longer travels straight up and down. Instead, it traces a diagonal zigzag pattern because the mirrors move to new positions between bounces. The diagonal path is longer than the vertical path, but light always travels at the same speed. A longer path at constant speed requires more time. Each tick of the moving clock takes longer than each tick of a stationary clock. This is not peculiar to this specific clock design. Any physical process that measures time shows the same effect. Chemical reactions, biological aging, radioactive decay, atomic vibrations, all of these slow down for moving objects. Time itself is slower, not merely clocks. Length contraction represents another major consequence. Objects moving relative to an observer are physically shorter in their direction of motion. This is not a visual illusion caused by light travel time. The object genuinely occupies less space. At 50% of light speed, an object contracts to about 87% of its rest length. At 99% of light speed, it compresses to roughly 14% of its original length. The Stanford Linear Accelerator in California is a straight tunnel about 3 kilometers long. Inside, electrons accelerate to velocities very close to light speed. From the electron's perspective, due to length contraction, the entire accelerator appears to be only about 50 centimeters long. The electrons experience themselves passing through a tunnel shorter than an arm's length, even though from our perspective the tunnel stretches 3 kilometers. From their reference frame, the tunnel truly is only 50 centimeters long. The universe does not privilege one viewpoint over another. A famous thought experiment called the ladder paradox illustrates the strangeness of this situation. Imagine a ladder longer than a barn. Someone runs through the barn carrying the ladder at relativistic speed. From the barn's perspective, the ladder contracts, and for a brief moment, the entire ladder fits inside with both doors closed. But from the ladder carrier's perspective, the barn is contracted, not the ladder, so the ladder should not fit. Both versions of events are simultaneously true. The resolution involves the relativity of simultaneity. What one observer sees as simultaneous, both doors closed at the same moment, is not simultaneous for the other observer. The universe remains consistent, but only if we abandon the idea that there exists a single universal present moment. The relativity of simultaneity may be the strangest consequence of all. Events that happen at the same time for one observer may not happen at the same time for another observer moving relative to the first. Einstein illustrated this with a thought experiment involving a train and lightning strikes. Imagine lightning strikes both ends of a moving train at exactly the same instant from the perspective of someone standing on a platform. That person sees both flashes simultaneously because light from each strike travels the same distance to reach them. But someone sitting in the middle of the train sees something different. The train is moving forward, so the light from the front strike has less distance to travel, while light from the rear strike must cover more distance. The passenger sees the front strike first. One might argue that this merely reflects light travel time, that the strikes really were simultaneous and the passenger simply sees them at different times. But special relativity provides no way to determine which observer is truly correct. Neither perspective is privileged. For the platform observer, the strikes are simultaneous. For the train passenger, they are not. No experiment, no measurement, no appeal to deeper reality can settle this dispute. This has far-reaching implications. There is no universal present moment. Different observers moving relative to each other literally inhabit different versions of now. British physicist Roger Penrose illustrated this with the Andromeda paradox. Imagine two people passing each other on a street. One walks slowly toward the Andromeda galaxy, about 2.5 million light-years distant. The other walks slowly in the opposite direction. Their relative velocities are tiny, perhaps a few kilometers per hour, but because of the vast distance involved, their planes of simultaneity are tilted relative to each other. What counts as now on Andromeda for one person differs from what counts as now for the other by several days. One person's present on Andromeda might include some event beginning, while the other person's present has that event already underway. Same moment on Earth, different events on Andromeda. This is not practically meaningful for everyday activities. The distances and speeds involved in daily life are too small for this effect to matter. But it reveals something profound about reality's nature. The present moment is not a single instant shared across the universe. It is observer-dependent. There is no cosmic now that everyone agrees upon. The twin paradox provides a famous illustration of time dilation. Imagine identical twins. One remains on Earth while the other boards a spacecraft and travels to a star 10 light-years away at 90% of light speed, then turns around and returns home. From Earth's perspective, the journey is straightforward. The star is 10 light-years distant. At 90% of light speed, the outbound trip requires about 11 years, the return trip another 11 years. Total elapsed time on Earth is roughly 22 years. But from the travelling twins' perspective, things differ. Because of length contraction, the distance to the star is not 10 light-years. At 90% of light speed with a Lorentz factor of about 2.3, the distance contracts to roughly 4.5 light-years. The trip takes correspondingly less time. Total elapsed time for the traveller is approximately 10 years. When the twins reunite, the travelling twin is about 12 years younger than the stay-at-home twin. They started the same age. Now one has aged significantly more than the other. They have experienced different amounts of time. This is not metaphor or illusion. The travelling twin genuinely aged less. Their heart beat fewer times. Their cells divided fewer times. They literally lived fewer years. This might seem paradoxical. If all motion is relative, why cannot the travelling twin claim that Earth moved away and returned, making the Earth twin younger? The resolution is that the situations are not symmetric. The travelling twin had to accelerate to leave Earth, decelerate and turn around, then decelerate again upon return. The stay-at-home twin remained in a single inertial reference frame throughout. Acceleration breaks the symmetry. This is not theoretical curiosity. Actual atomic clocks flown around the world on aircraft have shown exactly the time differences Einstein predicted. The twin paradox is simply how the universe operates. Another fundamental consequence states that nothing with mass can ever reach the speed of light. As an object speeds up, its kinetic energy increases. But in relativity, energy and mass are related. The more energy an object has, the more it effectively resists further acceleration. As the object approaches light speed, the energy required to accelerate it further increases without limit. Think of trying to accelerate a vehicle that becomes heavier the faster it goes. Initially, applying force produces significant acceleration. But as speed increases, each increment requires dramatically more energy. Eventually, infinite energy would be needed to reach the speed of light. That is not simply a large amount of energy. It is an amount that cannot exist. The speed of light is an asymptotic limit that can be approached but never reached. Accelerating just 1 kilogram of mass to 90% of light speed would require energy equivalent to about 25 megatons of TNT, more than the largest nuclear weapon ever detonated, and that only reaches 90%. Each additional decimal point requires exponentially more energy. Reaching exactly 100% would require literally infinite energy. The flip side is that particles without mass must travel at exactly the speed of light. They have no other option. Photons have no mass. They cannot travel at any speed other than light speed. They are created moving at that velocity and never slow down until absorbed. The relationship between energy, momentum, and mass in relativity demands this. For a massless particle, if it did not move at light speed, it would have zero energy, meaning it would not exist. Light does not merely happen to travel at a certain speed. It travels at the only speed physics allows for something without mass. The speed of light is not arbitrary. It is built into space-time structure itself. Understanding these effects requires thinking about space-time as a unified four-dimensional fabric. Common intuition treats space as three-dimensional and time as something separate, flowing independently in the background. Einstein showed they are connected, woven together into a single structure called spacetime. Hermann Minkowski, one of Einstein's former mathematics professors, did much to develop this mathematical framework. In 1908, Minkowski gave a famous lecture beginning with these words: "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." One useful visualization tool is the light cone. Imagine a point in space and time representing an event that happens at a specific place and moment. Now imagine all the light rays that could emanate from that event, spreading outward at light speed. In a diagram where time is vertical and space is horizontal, these light rays form a cone shape opening upward into the future. Everything inside that forward cone represents events that the original event could potentially influence. Light or anything slower could travel from the first event to the second. These events are called time-like separated, and the second event lies in the absolute future of the first. There is also a backward cone representing all events that could have influenced the original event. These lie in its absolute past. Everything outside both cones is called elsewhere. Events in the elsewhere region cannot be causally connected to the original event. Nothing can travel between them, not even light. For events in the elsewhere region, different observers will disagree about which happened first. The order of events outside one's light cone depends on one's motion. This is why light speed is sometimes called the speed of causality. It is the maximum rate at which cause and effect can propagate. It defines the boundaries of what can influence what. It determines which events lie in one's future, which in one's past, and which exist fundamentally disconnected in a cosmic elsewhere that can never be reached or influenced. The light cone also explains why faster than light travel would create catastrophic logical problems. Imagine sending a message faster than light to a distant star, arriving before light would have gotten there. Now imagine someone at that star moving relative to the sender at high speed. Because of relativity of simultaneity, there now differs from the sender's now. From their perspective, the faster-than-light signal might have arrived before it was sent. If they send a reply, also faster than light, that reply could arrive back before the original message was sent. One would receive an answer to a question not yet asked. This is called a causality violation and creates grandfather paradoxes, situations where effect precedes cause, potentially allowing prevention of events that already occurred. Most physicists believe faster-than-light travel is fundamentally impossible, not merely beyond current technology, but forbidden by space-time structure. The universe appears designed to prevent causal paradoxes. The speed of light is not merely a speed limit, but a causality limit, protecting the logical order of events across all spacetime. Experimental verification has confirmed Einstein's predictions repeatedly with exquisite precision. In October 1971, physicists Joseph Hafele and Richard Keating purchased seats on commercial airline flights and carried atomic clocks around the world. They flew eastward, then westward. Flying eastward, the planes moved in the same direction as Earth's rotation, increasing their speed relative to a cosmic reference frame. Flying westward, they moved against Earth's rotation, decreasing their effective speed. The predictions were specific. Eastward traveling clocks should lose about 40 nanoseconds relative to ground clocks. Westward traveling clocks should gain about 275 nanoseconds. The results confirmed Einstein's predictions. Eastward clocks lost 59 nanoseconds. Westward clocks gained 273 nanoseconds. Both results fell within predicted ranges. These are tiny time differences, less than a millionth of a second, but they were exactly what relativity predicted. This represented the first direct macroscopic demonstration that moving clocks truly run slow. The experiment cost only about $8,000, mostly for airline tickets. The clocks were given their own seats with tickets purchased under the name Mr. Clock. An even more dramatic demonstration occurs constantly in Earth's atmosphere. Moons are subatomic particles similar to electrons, but about 200 times heavier. They are unstable, decaying into other particles, with a half-life of about 2 microseconds when at rest in a laboratory. Cosmic rays constantly bombard Earth's atmosphere, creating moons about 10 kilometers up. At 2 microseconds per half-life, even traveling at light speed, moons should only travel about 600 meters before most decay. They should not reach the ground in significant numbers, but they do. Detectors measure many moons at Earth's surface. How is this possible? Time dilation. The moons travel at nearly light speed. From our perspective on the ground, their internal clocks run slowly. Their 2 microsecond lifetime stretches to many microseconds, giving them time to reach us. From the moon's perspective, the explanation differs but remains equivalent. They do not live longer than 2 microseconds by their own clocks. But from their viewpoint, Earth's atmosphere is length contracted. The 10 kilometers they must cross appears as only a few hundred meters. They easily complete the journey in their allotted lifetime. 2 completely different explanations, time dilation and length contraction, both giving the same answer. And that answer matches actual observations. Both explanations are correct in their respective reference frames and consistent with each other. This is what relativity demands, and this is what nature delivers. Perhaps the most practical everyday confirmation involves the global positioning system. GPS would not function without relativistic corrections. GPS operates by measuring the time for radio signals to travel from satellites to receivers. Each satellite carries atomic clocks. By comparing signals from multiple satellites, receivers can determine position to within a few meters. But satellites orbit at about 20,000 kilometers altitude, traveling approximately 14,000 kilometers per hour. Special relativity predicts their clocks should run slower than ground clocks by about 7 microseconds per day due to velocity. However, at that altitude, gravity is weaker. general relativity predicts clocks in weaker gravity run faster by about 45 microseconds per day. The net result is satellite clocks run about 38 microseconds per day faster than ground clocks. This might not sound significant, but light travels about 11 meters in 38 microseconds. Without relativistic corrections, GPS positioning errors would accumulate at about 11 meters per day. Within minutes, the system would become useless for navigation. The solution is elegant. GPS satellite atomic clocks are manufactured to tick at a slightly different frequency than ground clocks, pre-compensating for the relativistic time difference. Every GPS navigation relies on Einstein's relativity. If relativity were wrong, GPS would not work. Before leaving experimental verification, consider what happens when experiments seem to challenge relativity. In September 2011, collaboration measuring neutrinos traveling from CERN in Switzerland to Gran Sasso in Italy announced astonishing results. According to their measurements, neutrinos arrive 60 nanoseconds faster than light would have. If true, this would overturn everything discussed here. Faster than light travel would be possible, causality could be violated, and a century of physics would need revision. The physics community responded with intense scrutiny. In February 2012, the error was discovered. A loose fiber optic cable connecting the GPS receiver to the master clock had created a timing error. There was also a second error related to oscillator timing working in the opposite direction. The corrected results showed neutrinos arriving within the expected time frame, consistent with traveling at or very slightly below light speed. Einstein's theory survived. This episode demonstrates the scientific process. An extraordinary claim was made, subjected to rigorous examination, and the error found and corrected within months. Science works through this process of claim, scrutiny, and verification. The speed of light also has practical implications beyond GPS. Positron emission tomography, or PET scans, works through matter-antimatter annihilation. A patient receives an injection containing a radioactive tracer. The tracer emits positrons, which are antimatter electrons. When a positron encounters an ordinary electron, both particles completely annihilate. Their combined mass converts entirely into energy in the form of two gamma rays. Each gamma ray carries exactly 511,000 electron volts, precisely the mass energy of an electron or positron. The gamma rays fly off in exactly opposite directions. PET scanners detect these coincident gamma ray pairs. By tracing lines between coincident detections, the scanner can pinpoint where annihilation occurred, mapping metabolic activity. This is Einstein's mass-energy equivalence in medical practice. Every PET scan demonstrates that mass and energy are equivalent. At the other extreme, the Large Hadron Collider at CERN accelerates protons to speeds where relativistic effects dominate completely. The LHC is a ring about 27 kilometers in circumference. Protons circle this ring over 11,000 times per second, traveling at 99.999991% of light speed, moving just a few meters per second slower than light itself. At this speed, the Lorentz factor is approximately 7,460. The protons have roughly 7,400 times their rest mass in kinetic energy. From the proton's perspective, the entire 27-kilometer ring appears to be only about 4 meters around, contracted by relativity. When protons traveling in opposite directions collide head-on, The collision energy reaches 14 trillion electron volts. This is enough to create particles thousands of times heavier than protons, particles that have not existed naturally since the first moments after the Big Bang. The Higgs boson discovered at the LHC has a mass created purely from collision energy. Energy becomes matter exactly as Einstein's equation predicts. But light speed also imposes harsh limits. Consider communication with spacecraft. Light travels 300,000 kilometers per second. That sounds fast, but space is vast. The moon is about 380,000 kilometers away. Light takes 1.3 seconds to make the trip. A round-trip communication takes 2.6 seconds. Mars is much farther. At its closest approach to Earth, about 55 million kilometers, light takes about 4 minutes. A round-trip message takes at least 8 minutes. At its farthest, when Mars is on the opposite side of the Sun, about 400 million kilometers, one-way light travel time stretches to 22 minutes. The earliest possible answer to any question is 44 minutes later. This is not a technology problem solvable with better equipment. It is a fundamental feature of spacetime. The speed of light cannot be exceeded, so communication delays cannot be eliminated. The Voyager 1 spacecraft launched in 1977 is now about 170 astronomical units from Earth, roughly 25 billion kilometers. Light takes about 23 hours to reach Voyager 1. A command sent today arrives tomorrow. The nearest star system, Alpha Centauri, is about 4.2 light-years away, roughly 40 trillion kilometers. Any message would take more than 4 years to arrive. A conversation spanning over 8 years between exchanges is barely a conversation. The cosmic speed limit also determines what we can see. The universe is about 13.8 billion years old. Light that started traveling toward us 13.8 billion years ago has had that long to make the journey. This defines the edge of the observable universe, but the observable universe has a radius of about 46 billion light-years, not 13.8 billion. How can we see objects farther than light could travel in the universe's lifetime? The answer is that space itself has been expanding. Light that started its journey 13.8 billion years ago was much closer then. As it traveled, space stretched. The source of that primordial light has continued receding. By now, those early objects are 46 billion light-years away. The observable universe is therefore about 93 billion light-years in diameter. Beyond that boundary, light has not had time to reach us. Even stranger, distant galaxies are receding from us faster than light speed. This does not violate relativity. Special relativity says objects cannot move through space faster than light. It says nothing about space itself expanding. The galaxies are not flying through space at superluminal speeds. Space itself is stretching, carrying them along. Light from those galaxies emitted now will never reach us. We are fundamentally, irreversibly cut off from those regions of the universe. The cosmic speed limit also affects the search for extraterrestrial intelligence. If an alien civilization exists on a planet orbiting a star 100 light-years away, any signal they send takes 100 years to arrive. Any reply takes another 100 years. A single exchange spans 2 centuries. If the civilization is 1,000 light-years away, still within our own galaxy, a back-and-forth communication spans 2,000 years. The Roman Empire would have needed to start the conversation for us to be receiving replies now, and 1,000 light years is practically adjacent on cosmic scales. This creates what some scientists call the Great Silence. Even if the galaxy teems with intelligent life, the vast distances and light speed might make contact essentially impossible. Two civilizations might exist simultaneously in the Milky Way, both searching for each other, both sending signals, and never connect because signals have not had time to cross the intervening space. Perhaps someone is out there, but the universe is simply too large and the speed limit too strict for us to know. This isolation might be the natural state of intelligent beings in the universe, not because we are alone, but because the cosmic speed limit creates unbridgeable gulfs between stars. Every civilization might be an island, visible to others through telescopes, but forever beyond reach of conversation or visit. Given these restrictive limits, it is natural to ask whether any way around them exists. Scientists and science fiction writers have explored various possibilities. Most turn out to be impossible, but a few remain open questions. Quantum entanglement does not work for faster-than-light communication. When two particles become entangled, measuring one instantly affects what will be found when measuring the other, regardless of distance. Einstein called this spooky action at a distance. Many people think entanglement could enable faster-than-light communication. It cannot. When measuring an entangled particle, one gets a random result. One cannot choose the outcome. Neither party can tell whether the other has measured. The correlations between entangled particles only become visible when measurement results are brought together and compared, which requires normal light speed or slower communication. The spooky action creates correlations, not signals. There is a mathematical proof called the no communication theorem, demonstrating this rigorously. Quantum mechanics, despite its strangeness, respects light speed. Hypothetical particles called tachyons that travel faster than light face fundamental problems. Physicist Gerald Feinberg coined the term in 1967. Tachyons would have bizarre properties. They would have imaginary mass, meaning their mass squared would be negative. They would always travel faster than light, just as ordinary particles always travel slower. Adding energy would slow them down. Removing energy would speed them up. The problem is causality. If tachyons existed and could transmit information, they would enable signals to be received before being sent in certain reference frames. This creates logical paradoxes breaking physics consistency. No tachyons have ever been detected. Most physicists believe they do not exist. A more interesting possibility comes from general relativity. In 1994, Mexican physicist Miguel Alcubierre published a paper titled The Warp Drive, Hyperfast Travel Within General Relativity. He was directly inspired by Star Trek. Alcubierre showed that Einstein's equations permit a configuration where a bubble of flat space could move faster than light relative to distant observers. The bubble would not move through space at superluminal speeds. Instead, space itself would contract in front and expand behind. The ship inside would be locally stationary while the bubble carried it along. This technically does not violate special relativity, which prohibits objects from moving through space-time faster than light. The Alcubierre drive moves space-time itself. The catch is creating such a bubble would require exotic matter with negative energy density. In ordinary physics, energy is always positive or zero. Negative energy density would require something unlike any known material. Initial calculations suggested energy requirements equivalent to Jupiter's mass converted entirely to energy. Later refinements showed changing the bubble shape could dramatically reduce requirements, but dramatically reduced still means far beyond any imaginable technology. There are other problems. How would one steer such a bubble? How would one stop it? Light at the bubble's front could not reach the ship to bring information about obstacles ahead. The bubble might accumulate extremely high energy particles at its front edge, releasing them as a devastating blast when the drive disengaged. Wormholes represent another theoretical possibility. These are solutions to Einstein's equations connecting two distant points in spacetime through a shortcut, a tunnel through reality's fabric. Einstein and Nathan Rosen described these solutions in 1935. But the original Einstein-Rosen bridges are non-traversable. They collapse too quickly for anything to pass through. In 1988, physicist Kip Thorne and his student Michael Morris explored what it would take to create a traversable wormhole. They found that stabilizing a wormhole large enough to pass through would require negative energy equivalent to Jupiter's mass. If wormholes could be created and stabilized, they would raise the same causality concerns as any faster-than-light travel. If one end moved at high speed relative to the other, time dilation would cause the two ends to experience different amounts of time. Step through, and one might emerge in the past. The logical paradoxes would remain. There is one way to exceed light speed that is completely real and violates no physics. Traveling faster than light in a medium. Light travels at 300,000 kilometers per second in vacuum. But in other materials it travels slower. In water, light moves at about 225,000 kilometers per second, about 75% of vacuum speed. In glass, about 200,000 kilometers per second. In diamond, only about 125,000 kilometers per second. The ratio of light speed in vacuum to its speed in a medium is called the refractive index. Water has a refractive index of about 1.3. Glass is around 1.5. Diamond is about 2.4, which is why diamonds sparkle brilliantly. The high refractive index bends light sharply at surfaces, creating internal reflections. A charged particle moving through water faster than light moves through water creates an electromagnetic shockwave similar to a sonic boom. This phenomenon is called Cherenkov radiation and produces a characteristic blue glow. If one has seen photographs of nuclear reactor cooling pools, one has seen Cherenkov radiation. The water glows eerily blue because electrons from nuclear reactions travel faster than light travels in water. This does not violate relativity because the fundamental limit is light speed in vacuum. Particles can exceed the local speed of light in a medium while still traveling well below vacuum light speed. The electrons in reactor pools move at perhaps 60 or 75% of vacuum light speed, well below the cosmic limit, but still faster than light travels through water. Sometimes things in space appear to move faster than light without actually doing so. Astronomers observing certain quasars and radio jets have measured apparent velocities exceeding 10 times light speed. These are optical illusions created by geometry. When a jet of material moves at nearly light speed in a direction partly toward Earth, light travel time from different points along the jet gets compressed in an unintuitive way. The jet appears to cover more angular distance than it actually does. The true speed of material in these jets is around 99.7% of light speed. The superluminal appearance is a projection effect, not a physics violation. In 1999, Danish physicist Lene Vestergaard Hau achieved something remarkable. She slowed light to 61 kilometers per hour. Her technique involved passing light through an ultra-cold state of matter called a Bose-Einstein condensate. In this exotic state near absolute zero, the interaction between light and matter becomes extreme enough to bring light almost to a standstill. 61 kilometers per hour is 20 million times slower than light travels in vacuum. In 2001, Hau stopped light completely, holding it in place for a measurable time before releasing it to continue. In 2007, she demonstrated transferring a light pulse to a matter wave and back to light again. These experiments do not violate relativity. The fundamental speed limit is light and vacuum. What Hau demonstrated is that the interaction between light and matter can be manipulated to produce astonishing effects. But even stopped light in a Bose-Einstein condensate is not violating laws. The photons are being absorbed and re-emitted by atoms, creating an effective slowdown. The cosmic speed limit remains intact. Consider what light speed means for our place in the universe. We live in a cosmos of staggering size. The observable universe spans about 93 billion light-years, but everything beyond our cosmic neighborhood might as well be unreachable. Light from the Sun takes 8 minutes 20 seconds to reach Earth, crossing 150 million kilometers. We see the Sun as it was 8 minutes ago. If the Sun suddenly went dark, we would not know for over 8 minutes. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away, roughly 40 trillion kilometers. Light takes more than 4 years to make the journey. Even if we could build a spacecraft traveling at 10% of light speed, far beyond current technology, the trip would take over 40 years each way. The Milky Way galaxy spans about 100,000 light-years. Crossing from one side to the other, even at light speed, would take longer than modern humans have existed as a species. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years away. The light we see from Andromeda left when our ancestors were still developing the first stone tools. Any civilization in Andromeda looking at Earth now sees a planet without humans. This creates a peculiar cosmic isolation. We can see light from billions of galaxies but can never visit them, never communicate with anyone who might be there, never receive a reply within any human lifetime or any 1,000 human lifetimes. The speed of light also shapes what we can know about the universe. Because light takes time to travel, looking at distant objects means looking back in time. When we observe a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. Telescopes are time machines. This is useful for cosmology. We can study how the universe evolved by looking at objects at different distances, but it also means we can never see the universe as it currently is. Our view is always a composite of different ages, more recent nearby and more ancient farther away. Events are happening right now in distant galaxies that we will never see because the universe's expansion is carrying those galaxies away from us faster than light. Light emitted by those galaxies today will never reach us. We are forever cut off from most of the universe's current state. The speed of light does not merely constrain what we can do. It challenges the deepest assumptions about reality's nature. These are not abstract philosophical puzzles, but direct consequences of experimental facts. Time genuinely runs slower for moving objects. Space genuinely contracts. Events simultaneous for one observer are not simultaneous for another. These are not approximations. They are how the universe actually works. But if this is true, then many basic assumptions about reality must be wrong. We naturally think of time as a river flowing at a constant rate, carrying everyone forward together. We think of space as a fixed stage on which events play out. We think of now as a single moment everyone shares, spreading across the entire universe at once. Relativity tells us none of this is true. Consider what relativity of simultaneity really means. If there is no universal now, if different observers legitimately disagree about what is happening at this moment in distant places, then what is the present? Einstein himself took a radical position on this question. He came to believe in what philosophers call the block universe or eternalism. In this view, past, present, and future all exist equally. Spacetime is like a four-dimensional block with all events frozen in place. Our experience of now moving through time is an illusion, a peculiarity of consciousness, not a feature of physics. Einstein expressed this view movingly after the death of his lifelong friend Michel Fizeau in 1955. Einstein wrote to Fizeau's family, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Einstein died just weeks later. If his block universe view is correct, Fizeau and Einstein both still exist, frozen in the space-time of their lifetimes, as real as any moment we call present. The philosophical argument for the block universe draws directly from special relativity. Consider the Andromeda paradox again. Two people walking past each other on a sidewalk disagree about what is happening now on Andromeda. For one, a certain event has not happened yet. For the other, it has. Now ask which events are real. If we say only present events are real and future events have not happened yet, then we have a contradiction. An event cannot both have happened and not yet have happened. The only way to avoid this contradiction is to accept that both events, and indeed all events across all space-time, are equally real. Past, present, and future are all equally existent. What differs is only our perspective on them. Not all philosophers accept this conclusion. Some argue that there are ways to recover a meaningful present moment, even in relativity, perhaps by privileging a particular reference frame, or by accepting that reality is perspectival. These debates continue in philosophy, departments, and physics conferences. The growing block view accepts that past and present are real, but holds that the future is not yet determined. Under this view, the block of reality grows as time passes, with new events being added to the past. But this view struggles to explain why any particular moment should be the edge of the growing block, especially when relativity tells us different observers would place that edge at different points. Another approach called presentism insists that only the present moment is real. The past has ceased to exist, and the future does not exist yet. This matches intuitive sense of time, but seems hard to reconcile with physics. If only the present is real, who's present? The person walking toward Andromeda or walking away? What makes one perspective privileged over the other? Some physicists have proposed that relativity might be incomplete, that there could be a hidden preferred reference frame defining a universal present, even if we cannot detect it experimentally. But this seems like adding unnecessary complexity to explain away an uncomfortable conclusion. The honest answer may be that we simply do not know yet. The relationship between physics and the fundamental nature of reality remains one of the deepest unsolved problems in philosophy. What we can say is that light speed forces us to take these questions seriously. It is not mere speculation. The experimental facts demand that we revise our intuitive picture of time and space. It is striking that a measurement made by a Danish astronomer watching Jupiter's moons in 1676 would eventually lead to questions about whether the future already exists. The speed of light connects the everyday to the cosmic. Another philosophical puzzle concerns the nature of the speed limit itself. Why is light speed what it is? Why 300,000 kilometers per second rather than some other number? As far as physics can tell, it simply is. The speed of light is a fundamental constant of nature, not derivable from anything more basic. It appears in physics equations as a given, not as a consequence. Some physicists have speculated about varying light speed to see what would happen. A universe with a different value would have different chemistry, different stellar physics, different everything. In most such universes, complex structures like atoms and life could not exist. Our universe happens to have a speed of light compatible with our existence. This observation leads some to anthropic arguments. Perhaps there are many universes with different constants, and we necessarily find ourselves in one compatible with observers like us. Others find such arguments unsatisfying, hoping for a deeper explanation of why the constants have the values they do. For now, light speed remains a mystery at the deepest level. We know what it is. We know how it shapes physics, but we do not know why it has the particular value it does. There is also a philosophical puzzle about the light cone itself. Inside one's light cone, events are causally connected. Outside, they are not. Events in the elsewhere region cannot affect you, and you cannot affect them. They exist, but in a realm forever beyond your influence or knowledge, until they enter your past light cone. This means that right now, somewhere in the universe, events are occurring that will someday affect you, but that you currently have no access to whatsoever. And there are events that have occurred that you do not know about yet, that are racing towards you at light speed, whose effects you will experience in the future but cannot yet anticipate. In a sense, one's light cone defines the boundaries of existence. Everything that is you, everything that has made you, everything you will ever influence lies within that cone. Everything else might as well be in a different universe. Throughout this exploration, we have traced humanity's centuries-long effort to measure light speed and understand its consequences. In 1676, old Römer watched Jupiter's moons and realized light takes time to travel across space. His calculation was imprecise, but he proved the essential truth. Light, however fast, is not instantaneous. It took decades for Bradley to independently confirm this discovery. Over the next 2 centuries, Fizeau, Foucault, and Michelson refined measurements with increasing precision. By 1887, Michelson and Morley had shown that light travels at the same speed in all directions, regardless of Earth's motion. The ether did not exist. Something strange was occurring. In 1905, Einstein explained. He accepted light speed's constancy as a fundamental feature of nature and showed that time and space must be flexible to accommodate it. The resulting theory of special relativity revealed that moving clocks run slow, moving objects shrink, and simultaneity is relative. In the decades since, every prediction of relativity has been confirmed experimentally. Atomic clocks flown around the world show exactly the time differences Einstein predicted. Particles in accelerators live longer than expected because their time runs slow. GPS satellites require constant relativistic corrections to function. The equations are not merely mathematically elegant. They are accurate descriptions of how reality works. Light speed is not merely an interesting constant. It is woven into space-time structure. It connects mass and energy through Einstein's famous equation. It defines the boundary between what can influence what. It determines what we can see and what remains forever hidden. And it poses limits we may never overcome. We can approach light speed, but never reach it. We can look at distant galaxies, but never visit them. We can send messages to the stars, but never expect timely replies. Some find this sobering. The universe is vast and mostly unreachable. Even our nearest stellar neighbors are effectively isolated from us by light speed's tyranny. But there is another perspective. Light speed is not merely a barrier, but a window into reality's deepest structure. It teaches us that space and time are not the fixed stage we thought, but flexible, interconnected, responsive to motion and gravity. It shows us that mass and energy are two faces of the same thing. It reveals that causality itself has a speed limit, preserving the logical order of events across the cosmos. For millennia, humans assumed that time flows uniformly, that space is absolute, that distance is the same for everyone. Light speed showed us that none of these assumptions are true. Our everyday intuitions evolved on a small planet at a walking speed simply do not apply to the larger universe. Understanding this does not diminish our place in the cosmos. It deepens it. We are creatures who evolved to see the world in simple terms, and yet have developed the tools, mathematical and experimental, to perceive truths far beyond our sensory experience. We cannot feel time dilation, but we can measure it. We cannot see length contraction, but we can calculate its effects. We cannot travel at relativistic speeds, but we can understand what would happen if we did. Near the end of his life, Einstein reflected on that thought, experiment that had troubled him since adolescence. What would it be like to chase a beam of light? He never did get to ride alongside a light beam. No one ever will. But in trying to answer that question, he discovered something deeper than any journey could reveal. He discovered that the universe is stranger, more subtle, and more beautiful than anyone had imagined. Light speed does not merely tell us how fast light travels. It tells us what kind of universe we inhabit. And that universe, it turns out, is far more interesting than the simple, intuitive one we thought we knew. When looking up at the stars on a clear night, those points of light scattered across the darkness are distant suns, massive spheres of fusing hydrogen, each potentially hosting its own system of planets and moons. They are light years away, separated from us by distances so vast that the light entering one's eye has been travelling for years, decades, centuries, or even millennia. Some of that light began its journey before one was born. Some left its star before one's grandparents were born. Some has been travelling since before humans existed. We are connected to those distant stars across vast distances of space and time, linked by photons that have crossed the cosmic void to reach us. The universe is large beyond comprehension. Each person is small, a single individual on a single planet, but we are here and we can understand, at least conceptually, if not intuitively, what light speed really means. We can grasp that the universe is measured in these vast units. That space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend one's place in the cosmos, is something worth holding. The journey spans centuries. Ancient philosophers debated whether light was instantaneous or finite. Galileo attempted to measure light speed with lanterns on hilltops and failed. Romer tracked Jupiter's moons and made his bold prediction. Fizeau's toothed wheel caught returning light for the first time. Michelson and Morley conducted their careful experiment and found nothing. And then Einstein, a young patent clerk with no laboratory and no academic position, took that nothing and built from it a completely new understanding of space and time. An understanding so profound that even now, over a century later, it still challenges intuition. An understanding so accurate that we stake our lives on it every time we use GPS. The story of light speed is a story about human curiosity and persistence, about asking questions that seem unanswerable and finding ways to answer them, about following evidence wherever it leads, even when it leads to conclusions that contradict everything we thought we knew. The speed of light is 300,000 kilometers per second. It is a number, precise and exact, now fixed by definition. But what that number represents, the cosmic speed limit, the boundary of causality, the fabric of spacetime, is something far grander than any number can convey. Light speed breaks our everyday reality, but in doing so, it reveals a deeper reality, one where time bends, space contracts, and the cosmic speed limit preserves the order of cause and effect across all creation. That is not a limitation, that is a revelation, and perhaps most importantly, light speed connects us to the cosmos in a profound way. Every photon that enters one's eye has travelled at that exact speed. The light from the sun, the light from distant galaxies, the light from the cosmic microwave background at the edge of the observable universe. All of it has raced across space at exactly 300,000 kilometers per second. Not faster, not slower. That constancy, that reliability, that unchanging nature of light speed is one of the few things in the universe one can absolutely depend upon. And perhaps that is the true meaning of the speed of light. It is not merely a cosmic speed limit, but a fundamental constant that connects us to everything, everywhere, across all of time and space. In understanding it, we understand something essential about the universe itself and our place within it. Continuing from where the previous rewrite ended, the history of measuring light speed reveals something profound about the nature of scientific discovery itself. Progress often comes not from dramatic breakthroughs, but from patient accumulation of increasingly precise observations. Each generation of scientists refined the techniques of their predecessors, gradually narrowing the uncertainty until the measurements became so accurate that the value itself could serve as a fundamental definition. Consider the progression. Romer's initial estimate in 1676 was off by roughly 25%, yet it established the crucial principle that light speed was finite. Bradley's stellar aberration measurements in 1728 brought the error down to approximately 2%. Fizeau's terrestrial measurements in 1849 achieved accuracy within about 5%. Foucault improved this to less than 1% by 1862. Michelson's work in the late 19th century pushed precision to fractions of a percent. This pattern of refinement continued throughout the 20th century. As technology improved, so did measurement precision. Laser interferometry, atomic clocks, and sophisticated electronics allowed scientists to determine light speed with ever-decreasing uncertainty. By the 1970s, measurements had become so precise that the uncertainty in the speed of light was smaller than the uncertainty in the definition of the meter itself. This created an interesting situation. Scientists were measuring light speed by determining how far light traveled in a known time interval. But the accuracy of that measurement depended on how precisely the meter was defined. The meter had originally been defined as 1/10,000,000th of the distance from Earth's equator to the North Pole, a definition that seemed natural but was difficult to measure with high precision. Later definitions referenced specific physical standards, such as a platinum iridium bar kept in Paris. Eventually, scientists realized they were approaching the problem backward. Instead of using the meter to measure light speed, it made more sense to use light speed to define the meter. Light's constancy across all reference frames, proven by countless experiments, made it a more fundamental standard than any physical object or planetary dimension. The decision in 1983 to fix light speed by definition represented a philosophical shift in how we think about measurement standards. Rather than basing our system on arbitrary choices or local planetary characteristics, we ground it in fundamental properties of the universe itself. The meter is now defined as the distance light travels in vacuum during 1/299,792,458th of a second. This definition makes light speed exact by definition, but it transfers any measurement uncertainty to other quantities. When we measure the length of an object, we are effectively measuring how long it takes light to traverse that distance. The speed of light has become a conversion factor between space and time, both conceptually and practically. This interchangeability between space and time measurements reflects the deeper unity that Einstein's relativity revealed. Space and time are not separate entities, but aspects of a single four-dimensional continuum. Measuring distance and measuring time are fundamentally the same type of measurement in different directions through space-time. The implications extend beyond mere measurement standards. If space and time are unified, then events in the universe cannot be neatly separated into spatial relationships and temporal sequences. The order of events depends on motion through space-time, not on some absolute cosmic clock. The location of events depends on when they occur relative to an observer's motion, not on some fixed coordinate grid. This unity of space-time also affects how we think about motion itself. When an object moves through space, it also moves through time. But there is a trade-off. The faster something moves through space, the slower it moves through time. Everything moves through space-time at the same total speed, but motion can be distributed differently between the space dimensions and the time dimension. Massless particles like photons move through space at the maximum possible speed, which means they do not move through time at all. From a photon's perspective, if such a thing can be said to exist, no time passes during its journey. A photon emitted from a distant galaxy billions of years ago experiences no elapsed time before being absorbed by a telescope detector. Its entire existence, from emission to absorption, occurs in a single instant from its own frame of reference. This leads to a peculiar conclusion. Photons do not age. They do not experience duration. The entire history of the universe, from the moment they were created until they are destroyed, passes in what would be for them a timeless instant. The photon carries information about the conditions at its creation, preserved perfectly, because for the photon, no time has elapsed since that creation. For objects with mass, the situation differs. They cannot reach light speed, so they always move through time as well as space. The distribution between spatial motion and temporal motion determines their trajectory through space-time. Objects at rest relative to an observer move purely through time from that observer's perspective. Objects in motion move through both space and time. The concept of proper time becomes important here. Proper time is the time measured by a clock traveling with an object, the time experienced by the object itself. Different paths through space-time correspond to different amounts of proper time. A clock that remains stationary experiences more proper time than a clock that makes a high-speed journey and returns. Both clocks trace paths through space-time from one event to another, but the length of these paths measured in proper time differs. This property of space-time is sometimes called the twin paradox, though as we have discussed, it is not truly paradoxical. The resolution lies in recognizing that different paths through space-time have different lengths when measured in proper time. Just as two different routes between two cities can have different distances, two different paths through space-time between two events can have different durations of proper time. The geometry of space-time differs from the geometry of ordinary space in an important way. In ordinary space, a straight line is the shortest distance between 2 points. In space-time, a straight path through time is the longest duration of proper time between two events. The traveling twin takes a path that involves acceleration and high velocity, which corresponds to a shorter proper time than the stay-at-home twin's straight path through time. This difference in geometry arises from the negative sign in the space-time metric, the mathematical expression that defines distances in space-time. Time contributes to the space-time interval with the opposite sign from space. This mathematical peculiarity reflects the physical fact that space and time, while unified, are not equivalent. They play different roles in the structure of reality. The light cone structure that emerges from this geometry has profound implications for causality. Events outside each other's light cones cannot causally influence each other. The future light cone of an event contains all events that could potentially be affected by it. The past light cone contains all events that could have influenced it. Everything else lies in a region sometimes called the absolute elsewhere, causally disconnected from the event. This structure ensures that cause precedes effect for all observers, even though different observers may disagree about simultaneity. If two events are causally connected, all observers will agree about their temporal order. If one event caused another, that causal relationship remains invariant under changes of reference frame. The speed of light, by setting the boundary of the light cone, protects causality from paradox. Consider what would happen if faster than light signaling were possible. Suppose an observer could send a message that arrived at its destination before light would have gotten there. From that observer's reference frame, the message travels forward in time. But from another observer's reference frame, moving at high velocity relative to the first, the message might arrive before it was sent. This is not a mere appearance, but a real feature of how simultaneity works in relativity. If the recipient then sent a reply using the same faster-than-light method, that reply could arrive back at the original sender before the original message was sent. The sender would receive a response to a message not yet transmitted. This creates a causal loop, a sequence of events that includes its own cause. Such loops lead to logical contradictions, situations where effects can prevent their own causes. Most physicists believe the universe does not permit such contradictions, which suggests that faster-than-light signaling is fundamentally impossible. The speed of light serves as a cosmic sensor, preventing causal paradoxes by limiting how fast information can propagate. This censorship is not arbitrary, but built into the geometry of spacetime itself. The relationship between information and causality deserves closer consideration. Information, in the physical sense, requires a causal connection. For information about an event to reach an observer, some physical process must carry that information from the event to the observer. Light is one such carrier, but any physical signal will do. All such signals propagate at or below light speed. This limitation affects not just communication, but also the very concept of knowledge about distant events. We cannot know the current state of distant objects because information about their current state has not had time to reach us. We can only know their past state, and we cannot even agree with other observers about which past state we are observing. The observational present, the collection of events we consider to be happening now, is not a universal present, but a personal present determined by our state of motion. Different observers have different observational presence. An observer moving toward a distant star considers events at that star to be happening now that have not yet entered the observational present of an observer moving away from that star. This relativity of the present has deep philosophical implications. If the present is observer-dependent, then the distinction between past, present, and future cannot be a fundamental feature of reality. Different observers partition space-time into past, present, and future in different ways. What is present for one observer lies in the past or future for another. Yet all observers coexist in the same universe, experiencing the same physical reality. Einstein's block universe interpretation attempts to resolve this apparent contradiction by asserting that all of space-time exists equally. Past, present, and future are all equally real, equally existent. Our perception of time flowing, of the present moment advancing, is a feature of consciousness rather than physics. We experience space-time one moment at a time, but all moments exist simultaneously in the four-dimensional structure of reality. This view faces philosophical challenges. If the future already exists, then is it predetermined? Do we have free will, or are our actions already fixed in the space-time structure? These questions touch on deep issues in philosophy of mind and metaphysics that physics alone can't resolve. Physics can describe how space-time works, but it cannot tell us what this implies about consciousness, choice, or the nature of existence. Some philosophers reject the block universe, arguing for presentism or the growing block view. Presentism asserts that only the present exists, that past events have ceased to be real and future events do not yet exist. The growing block view holds that the past and present are real, but the future is not yet determined, that reality grows as time passes. Both alternatives face challenges from relativity. If only the present is real, who's present? Different observers moving relative to each other have different presents. Does reality differ for different observers? Or is there a privileged reference frame that defines the true present? Special relativity seems to deny any such privileged frame. All inertial reference frames are equally valid. The growing block view faces similar problems. Different observers would disagree about where the edge of the growing block lies, about which events have already happened and which have not. The block would have to grow differently for different observers, which seems conceptually problematic. How can reality grow in multiple inconsistent ways simultaneously? These philosophical difficulties do not invalidate the physics. Relativity makes predictions that can be tested experimentally, and those predictions have been confirmed countless times. The philosophical interpretation of what relativity means for the nature of time and reality remains open to debate, but the physical facts are well established. Perhaps the lesson is that our intuitive concepts of time, developed through everyday experience, simply do not apply at a fundamental level. The universe may not care about our philosophical categories. It behaves according to mathematical laws that can be precisely formulated and experimentally tested. Our task is to understand those laws and their implications, even when they challenge our preconceptions. The constancy of light speed, the unity of space-time, the relativity of simultaneity. These are not philosophical speculations, but empirical facts about our universe. They have been tested in countless experiments over more than a century. They form the foundation of modern physics and underlie technologies we use daily. GPS navigation depends on them. Particle accelerators operate according to their principles. Time synchronization systems account for their effects. Beyond these practical applications, understanding relativity deepens our appreciation of the universe's structure. Space and time are not the simple, absolute entities they appear to be in everyday life. They are dynamic, interconnected aspects of a four-dimensional whole. The relationships between events depend on motion and perspective. Causality flows along paths determined by light cones. The distinction between space and time is relative rather than absolute. Light itself occupies a special place in this structure. Massless and moving at the ultimate speed, light defines the boundary between past and future. Light rays trace out the edges of light cones, separating events that can causally influence each other from those that cannot. Every photon travels along what is called a null geodesic, a path through space-time that has zero length when measured by the space-time metric. This zero length might seem strange. How can light travel vast distances yet have zero space-time interval? The resolution lies in how space-time distance is measured. The space-time interval between two events involves both the spatial distance and the time interval between them. For light, these two contributions exactly cancel. The spatial distance light travels always equals the speed of light multiplied by the elapsed time, and the mathematical form of the space-time metric ensures this results in zero total interval. Objects with mass travel along time-like paths with positive space-time interval. The interval represents the proper time experienced by an object traveling that path. Massive objects cannot follow null paths because they cannot reach light speed. Photons must follow null paths because they have no mass. The dividing line between time-like and null paths represents the cosmic speed limit. This geometric perspective reveals why the speed of light is invariant. Light follows null paths by definition. A null path remains null regardless of reference frame. The statement that light travels at speed c in all reference frames is equivalent to stating that null paths are preserved under changes of reference frame. This preservation is built into the structure of space-time transformations, the Lorentz transformations that relate different inertial reference frames. The Lorentz transformations have a mathematical structure that preserves the space-time interval. If two events are separated by a particular space-time interval in one reference frame, they are separated by the same interval in all reference frames. This invariance of the space-time interval implies the invariance of light speed and accounts for time dilation and length contraction. Time dilation and length contraction are not independent phenomena, but two aspects of a single geometric fact. When an object moves, its path through space-time tilts relative to an observer's time axis. This tilt causes the object's time direction to appear partially spatial from the observer's perspective, leading to time dilation. Similarly, the object's spatial extent appears partially temporal, leading to length contraction. Both effects arise from the geometry of space-time and the angle between different observers' reference frames. The magnitude of these effects depends on the velocity. At low velocities, much smaller than light speed, the tilt is small and the effects are negligible. As velocity approaches light speed, the tilt becomes more pronounced and the effects grow larger. At light speed itself, the tilt would be complete. Time would be entirely spatial and space entirely temporal from the moving object's perspective. But this limiting case cannot be reached by massive objects. The energy required to accelerate an object grows without bound as velocity approaches light speed. At 90% of light speed, an object's kinetic energy is roughly twice its rest mass energy. At 99%, the kinetic energy exceeds 6 times the rest mass energy. At 99.9%, it reaches 22 times the rest mass energy. Each additional 9 in the percentage requires far more energy than all the previous acceleration combined. This escalating energy requirement makes light speed an insurmountable barrier for massive objects. No finite amount of energy can accelerate mass to light speed. The universe imposes an absolute speed limit, not through any force or resistance, but through the structure of space-time itself. Attempting to reach light speed is not like running into a wall, but like trying to reach infinity. The closer you get, the farther you still have to go. Particles without mass face the opposite constraint. They must travel at light speed. They cannot slow down or stop. Photons are created moving at light speed and continue at that speed until absorbed. Other massless particles, if they exist, would behave similarly. The Distinction between massive and massless particles is fundamental, dividing objects into those that experience time and those that do not. Neutrinos were long thought to be massless, traveling at light speed like photons. But experiments in the late 20th century revealed that neutrinos have tiny but non-zero masses. This discovery had profound implications. If neutrinos have mass, they must travel slightly slower than light. The difference is minuscule. Neutrinos move at something like 99.9999999% of light speed. But it is real and has important consequences for particle physics and cosmology. The question of whether any truly massless particles exist besides photons remains open. The standard model of particle physics predicts the existence of several massless particles, including photons and gluons, the carriers of the strong nuclear force. Gravitons, if they exist as quantum particles carrying the gravitational force, should also be massless. But we have never directly detected individual gluons or gravitons, so their properties remain somewhat theoretical. The relationship between mass and the speed limit reveals something deep about the nature of mass itself. Why do some particles have mass while others do not? The answer, according to the standard model, involves the Higgs field, a field permeating all of space that interacts with particles to give them mass. Particles that interact strongly with the Higgs field have large masses. Particles that do not interact with it at all have zero mass and travel at light speed. The discovery of the Higgs boson at CERN in 2012 confirmed this picture. The Higgs boson is an excitation of the Higgs field, a quantum of the field, in the same way a photon is a quantum of the electromagnetic field. By creating and detecting Higgs bosons, physicists verified that the Higgs field exists and operates as theoretically predicted. This discovery completed the standard model, the comprehensive theory describing all known particles and forces except gravity. The standard model is one of the most successful theories in physics, making predictions that have been verified to extraordinary precision. Yet it leaves many questions unanswered. Why do particles have the particular masses they have? Why does the Higgs field exist? What is the nature of dark matter and dark energy? How does gravity fit into the quantum framework? These questions push us toward the frontiers of current physics research, where light speed continues to play a central role. String theory, one approach to unifying quantum mechanics and gravity, is formulated in a spacetime where light speed is a fundamental constant. Loop quantum gravity, an alternative approach, builds spacetime itself from quantum building blocks while preserving the light cone structure and the cosmic speed limit. Both approaches face the challenge of making testable predictions. The energy scales where quantum gravity effects become important are far beyond what we can access in particle accelerators. The Planck energy, the characteristic energy scale of quantum gravity, is roughly 10 to the 19th billion electron volts, about a quintillion times higher than the energies achieved at the Large Hadron Collider. At these enormous energies, space-time itself might behave in unexpected ways. Some theories suggest that space-time has a discrete structure at the Planck scale, that there is a smallest possible distance and a shortest possible time. If so, the smooth space-time of general relativity would be an approximation, valid at large scales, but breaking down at the smaller scales. Such a discrete structure might affect the propagation of light. If space-time is grainy at the Planck scale, light traveling cosmological distances might accumulate tiny delays depending on its energy. High-energy photons might travel slightly slower than low-energy photons. This effect would be incredibly small, but potentially detectable by observing gamma rays from distant cosmic events. Observations of gamma-ray bursts, the most powerful explosions in the universe, have searched for such energy-dependent delays. So far, none have been detected. Photons of all energies arrive simultaneously from these distant events to within the measurement precision. This suggests that if space-time has a discrete structure, it must be even finer than some theories predict, or the effects must not accumulate in the way theorists expected. These null results do not disprove quantum gravity theories, but they constrain them. Any viable theory must explain why light propagates through space-time with such consistent velocity, regardless of energy. The constancy of light speed, proven by Michelson and Morley in the 19th century and confirmed by countless experiments since, remains one of the most precisely verified facts in physics. This constancy has been tested not just on Earth, but across the observable universe. Observations of distant quasars and galaxies show that light behaved the same way billions of years ago as it does today. Spectral lines from distant atoms have the same patterns as spectral lines from nearby atoms, indicating that the laws of electromagnetism, and therefore the speed of light, have remained constant over cosmic time. Some alternative cosmological theories propose that physical constants, including light speed, might have changed during the universe's evolution. These theories attempt to explain certain cosmological puzzles, such as the horizon problem or the flatness problem, by allowing constants to vary. But observations strongly constrain any such variation. If light speed has changed, it has changed by less than a few parts per million over billions of years. The extreme constancy of light speed across space and time underscores its fundamental nature. This is not merely a property of photons, but a feature of space-time, geometry itself. The speed of light is the conversion factor between space and time, the rate at which clocks tick relative to rulers. Changing light speed would mean changing the relationship between temporal and spatial measurements, altering the very structure of space-time. This immutability provides a stable foundation for physics. In a universe where fundamental constants wandered randomly, it would be difficult to formulate lasting physical laws. The constancy of light speed and other fundamental constants like the electric charge and Planck's constant allows patterns to persist, enabling the complex structures and processes that make up our universe, including life and consciousness. The anthropic principle suggests one possible explanation for this constancy. Perhaps universes with different values of fundamental constants can exist, but only in universes with appropriate values can complex structures form. We necessarily find ourselves in a universe compatible with our existence, which requires constants in certain ranges. This selection effect could explain why our universe has the particular properties it does. Critics argue that the anthropic principle is not truly explanatory. It describes a selection effect but does not explain why different universes would have different constants, or what mechanism generates this ensemble of universes. The multiverse hypothesis, which posits that our observable universe is one of many universes with varying properties, faces similar criticisms regarding testability and explanatory power. Regardless of these deeper questions, we can investigate the physics of our universe as we find it. Light speed is what it is, approximately 300,000 kilometers per second, and this value determines much about how the universe operates. The finite speed limit creates light travel time delays, limiting how quickly information can propagate. It creates light cones that structure causality. It unifies space and time into spacetime. It ensures that energy and mass are equivalent. It prevents causal paradoxes. These consequences shape the universe at every scale. At the scale of human experience, relativistic effects are small but measurable. GPS satellites must account for time dilation. Particle accelerators must account for increasing mass at high velocities. High-precision clocks show time dilation effects even from driving around in a car. At the scale of the solar system, light travel time becomes significant. Commands sent to space probes experience delays of minutes to hours. We see planets as they were minutes ago, not as they are now. The finite speed of light makes real-time interaction with distant objects impossible. At stellar scales, light travel time measures years. The light from the nearest star took over 4 years to reach us. We see that star as it was 4 years in the past. Any changes happening there now will not be visible to us for 4 years. This creates a kind of observational isolation where distant simultaneous events are fundamentally unknowable. At galactic scales, light travel time spans thousands or millions of years. The Milky Way galaxy is about 100,000 light-years across. Light from stars on the far side of the galaxy shows us how those stars appeared 100,000 years ago. The galaxy we observe is a patchwork of different times, with nearby regions showing recent conditions and distant regions showing ancient conditions. At cosmological scales, light travel time approaches the age of the universe itself. The most distant galaxies we observe emitted their light more than 13 billion years ago, when the universe was young. We see them as they were in that ancient era, not as they are today. We have no way to know their current state. The light showing their current condition has not yet had time to reach us and will not reach us for billions of years. This delay creates a kind of temporal gradient in our observations. The farther out we look, the farther back in time we see. Telescopes are time machines, showing us the universe's history by capturing light from progressively more distant eras. By observing galaxies at different distances, astronomers can trace how the universe has evolved over cosmic time. This observational window into the past has revealed much about cosmic history. Early galaxies appear different from modern galaxies, smaller and more irregular. The rate of star formation was higher in the early universe than it is now. The abundance of heavy elements has increased over time, as stars have processed light elements into heavier ones. The universe has been expanding throughout this time, causing distant galaxies to recede from us. The expansion of space itself adds another layer of complexity to understanding light's journey across cosmic distances. As light travels through expanding space, the space through which it moves stretches. This stretching lengthens the light's wavelength, shifting it toward the red end of the spectrum. This cosmological redshift provides a measure of how much the universe has expanded during the light's journey. Distant galaxies show larger redshifts, indicating they are receding faster. The relationship between distance and recession velocity is approximately linear for relatively nearby galaxies, a pattern known as Hubble's law. More distant galaxies deviate from this simple relationship in ways that reveal how the expansion rate has changed over cosmic history. Current observations indicate the expansion is accelerating, driven by something called dark energy that pervades space and exerts a kind of anti-gravity. This acceleration means that galaxies beyond a certain distance are receding faster than light speed due to the expansion of space between us. This does not violate relativity because the galaxies are not moving through space faster than light. Rather, space itself is expanding, carrying them along. Light from these ultra-distant, rapidly receding galaxies will never reach us if emitted now. We are already seeing the most distant light we will ever see from those galaxies. As time goes on and acceleration continues, more galaxies will cross beyond our cosmic horizon, disappearing from our observable universe in the far future. Assuming dark energy remains constant, our observable universe will contain only the local group of gravitationally bound galaxies. All other galaxies will have receded beyond detectability. This raises a sobering possibility. Future civilizations arising billions of years from now might look out at the universe and see only their local cluster of galaxies. The evidence for cosmic expansion, for the Big Bang, for the existence of distant galaxies would be gone, carried away by the expansion itself. Those future civilizations might conclude they lived in a static island universe, unaware of the vast cosmos beyond their observational reach. We are fortunate to exist at a cosmic epoch where the evidence of the universe's true nature remains visible. We can see the cosmic microwave background, the afterglow of the Big Bang. We can observe distant galaxies and trace cosmic history. We can measure the expansion rate and dark energy. Future observers might lack this privilege, trapped in an observational horizon that hides most of reality from view. This thought experiment illustrates an important epistemological point. What we can know about the universe depends on what information can reach us. Light's finite speed limits this information flow, creating horizons beyond which knowledge can't extend. We accept this limitation as observers in our particular cosmic era and location. But we must remember that our observations show us only a portion of reality. The universe undoubtedly extends beyond what we can observe. The observable universe, the region from which light has had time to reach us, is finite, but the entire universe may be infinite. We cannot know what lies beyond our cosmic horizon. There may be infinite space filled with galaxies, stars, and planets we can never observe. Or the universe may curve back on itself in some higher dimension, making it finite but unbounded, like the surface of a sphere. These questions about the universe's global structure may be fundamentally unanswerable if they lie beyond our observational horizon. We can formulate theories and make predictions, but we cannot test those predictions if the relevant evidence is causally disconnected from us. Light's finite speed, which allows us to see into the past and trace cosmic history, also limits how much of the universe we can ever access. Within these limitations, we can still investigate an enormous domain. The observable universe contains hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of these stars likely have planets. Some of those planets may harbor life. The question of whether we are alone in the universe remains one of the most profound mysteries we face. The search for extraterrestrial intelligence must contend with light's finite speed. If alien civilizations exist on planets orbiting distant stars, any signals they send will take years, centuries, or millennia to reach us. Our response will take equally long to return. A conversation with aliens 1,000 light-years away would span 2,000 years per exchange. The Roman Empire would need to have initiated the conversation for us to be receiving replies today. This communication barrier might explain the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the absence of evidence for them. Perhaps civilizations are common, but the vast distances and long light travel times make contact effectively impossible. Each civilization might exist in effective isolation, aware of the abstract possibility of others, but unable to make meaningful contact. Alternatively, technological civilizations might be rare or short-lived. The window during which a civilization possesses radio technology but has not yet destroyed itself or moved beyond detectable communication methods might be brief on cosmic timescales. If that window is only a few centuries, and civilizations are separated by thousands of light years, the chance of overlap is small. These speculations remain just that, speculations. We have no direct evidence for extraterrestrial life of any kind, let alone technological civilizations. The search continues through various programs that scan the sky for artificial radio signals or other signs of technology. So far, these searches have found nothing definitive, leaving the question open. Regardless of whether other intelligent life exists, we can appreciate our own remarkable position. We are matter that has become conscious, able to contemplate the universe that created us. We have uncovered deep truths about space, time, matter, and energy through observation and reason. We have measured the speed of light, discovered its constancy, and understood its implications for the structure of reality. This understanding represents one of humanity's greatest intellectual achievements. From ancient philosophers speculating about light's nature through centuries of increasingly precise measurements, to Einstein's revolutionary insights and modern experimental confirmations, the story of light speed illustrates the power of the scientific method. Observation, hypothesis, prediction, and test. This cycle has revealed truths about the universe that would seem incredible without the evidence to support them. Time genuinely slows for moving objects. Space genuinely contracts. Simultaneity is genuinely relative. These are not philosophical abstractions, but physical facts with practical consequences. GPS navigation depends on them. Particle physics requires them. Every high-precision time measurement confirms them. The universe operates according to these principles, whether or not they match our everyday intuitions. Perhaps the deepest lesson is that reality transcends intuition. Our brains evolved to navigate a world of moderate speeds, sizes, and energies. The universe extends far beyond this narrow range, encompassing velocities approaching light speed, distances spanning billions of light years, energies dwarfing anything in everyday experience. At these extremes, reality behaves in ways our intuitions never anticipated. Yet through mathematics and experimentation, we can understand these extreme regimes. We can formulate precise theories, make quantitative predictions, and test them against observation. We can extend our knowledge far beyond direct experience, mapping territories our ancestors could never have imagined existed. This is the triumph of science, the systematic extension of human understanding to encompass all of reality, not just the small corner we directly inhabit. Light's speed connects all of these domains. It appears in the equations governing electromagnetism, determining how charged particles interact. It appears in the equations of special relativity, linking space and time. It appears in Einstein's famous equation relating mass and energy. It appears in quantum field theory, setting the scale for particle interactions. It appears in cosmology, determining cosmic horizons and light travel times. This universal constant threads through physics, connecting disparate phenomena and revealing hidden relationships. The fact that one number appears in so many contexts suggests a deep unity in nature's laws. The speed of light is not arbitrary but fundamental, woven into the structure of physical law at the most basic level. As we continue exploring the universe and probing nature at smaller scales and higher energies, light speed will undoubtedly remain central to our understanding. Whatever new phenomena we discover, whatever new theories we develop, they must be consistent with the constancy of light speed and its implications. This requirement provides a powerful constraint, guiding theoretical developments and eliminating proposals that cannot accommodate this fundamental fact. The journey that began with Römer observing Jupiter's moons continues today in laboratories and observatories worldwide. Each new experiment refines our understanding. Each new observation extends our knowledge. The speed of light, once uncertain by 25%, is now known to more than enough precision for any conceivable application. The effects it governs, once surprising and counterintuitive, are now routine in high-precision technology. Yet mysteries remain. We do not fully understand why light speed has the particular value it does. We do not know whether it is truly constant at all scales and in all conditions. We do not know how to reconcile the continuous spacetime of relativity with the quantum mechanics that govern small scales. We do not know what dark energy is or why cosmic expansion accelerates. We do not know whether physics beyond the standard model exists at accessible energies. These open questions ensure that physics remains a vibrant, active field of inquiry. Our understanding continues growing, building on the foundation laid by our predecessors. Each generation adds new knowledge, new techniques, new perspectives. The story of light speed is not finished, but ongoing, a chapter in humanity's larger quest to understand the cosmos. In contemplating this quest, we might feel both humbled and elevated, humbled by the vast scales of space and time that dwarf human existence, elevated by the power of human reason to comprehend these scales and uncover the laws governing them. We are tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, yet we can understand the structure of space-time and the behavior of matter and energy across the entire observable universe. This capacity for understanding distinguishes us and gives our existence meaning. We are not merely passive observers, but active participants in the universe's self-understanding. Through us, the universe contemplates itself, discovering its own properties and history. This perspective provides a sense of connection to something larger, a reminder that we are integral parts of the cosmos, not separate from it. As we close this exploration of light speed and its implications, we can appreciate both what we have learned and what remains to be discovered. The speed of light is both a simple number and a profound constant. both easily measured and deeply mysterious. It limits how fast we can travel and communicate, yet connects us to the most distant reaches of space and time. It breaks our everyday reality, revealing a deeper, stranger, more beautiful universe than we could have imagined. This deeper universe is the one we actually inhabit. Understanding it changes how we see everything. The stars we observe at night are not merely distant lights, but windows into the past, showing us the universe as it was years or centuries or millennia ago. The ground beneath our feet is not merely solid matter, but a vast collection of atoms, held together by forces that ultimately derive from the same principles governing light and space-time. We are made of this material, subject to these laws. We are space-time thinking about itself, matter contemplating its own nature. In understanding light speed and its consequences, we understand something fundamental about ourselves and our place in existence. This understanding enriches experience, deepening our appreciation for the beauty and subtlety of the world around us. Light speed remains constant, unchanging across all of space and time as far as we can measure. This constancy provides stability in an otherwise changing universe. Stars are born and die. Galaxies collide and merge. The universe expands and evolves. But through it all, light travels at the same unwavering pace, 300,000 kilometers per second, the ultimate speed limit, the boundary of causality, the thread connecting past to future across all of space and time.